Good morning. Apologies for my voice. Coming out at the end of a cold, but my real voice doesn't sound any better. So um, so today I'm going to talk about big data. That's my job. That's what I was trained to do. That's all my projects are. But my wife thinks I have something called opposition disorder. So today I'm going to conflict with myself about. I'm going to make the big data feel a little bit small, and I'm going to articulate why, and I hope that it will come across. So what we are faced actually is big data is big, but there's something about decision space that we have to start looking. Actually, the more data we have, the more choices we have, I would submit, and then the more decisions we need to make, and the difference between good decision and a bad decision will differ a lot. But before I even do that, I want to go back and respect the big data. I'm going to go back all the way to 1982. And I'm going to talk about the technology, what we had there, and I have a gadget today that I brought. So back in 1980s, this is me, actually. And I look pretty good. Look at the hair, and I don't have less hair, I have no hair now. You could argue this is linked to the decisions we all make, and that's the actually heart of this talk. But I want to start with this. This computer is called Sinclair ZX Spectrum. I see some members in the audience, they might actually had this one, and I'm not going to point out. That will be a little bit more revealing your age here. But there's something unique about the machine I'm holding in my hand. This is my first computer. This is not a replica I bought from eBay. This is the one that I actually had it when I was this guy back then. 1985, my first computer, Sinclair ZX Spectrum. Tim, may I ask you to send around that? Maybe some of the audience would have nostalgia with it. So, Sinclair ZX Spectrum, 1982, beautiful machine, 40 rubber keys, very, very touchy-feel rubber keys. It had 48 kilobytes of memory. Okay, let's think about that. 48 kilobytes of memory. So for those of you digital photographers, if I took a picture of you, it would maybe store Tim's left eye. That's it. Like, it's not going to get any of us. But I'm not belittling this. There is so much I did with this machine. I programmed in a language called BASIC. I play a ton of computer games. My children think that their games are a lot better. Well, actually, it's not that much better. Now, there's more resolution to it, but they do less with imagination. But I'll leave it at that. But think about 48 kilobytes. You could not actually, it doesn't have a hard drive. Okay, the only way you put this is that, okay, you guys are thinking, how many more, I have nothing else in my pocket. This is a cassette tape. You can only load your computer program, a game with a cassette tape, or when you're finished coding your basic program to do whatever you want, you couldn't turn off your computer. You need to put it back to the cassette tape, rewind it, and you would be able to store it. Now, but I'm not belittling this, actually. I'm going to come today, this age. Okay? And this is my iPhone. Okay? Many of you guys have the iPhones in there. Just to compare this, it's one of the newer ones, iPhone 11. I don't know if you guys are up to that. 512 gigabytes of memory. So let me actually make a comparison. 48 kilobytes. Kilo is 1,000. Mega is a million. Giga is a trillion, billion. So this machine, my phone, has 10 million times more memory than my beautiful Sinclair ZX Spectrum. 10 million is awesome. Think about it. Actually, I did a little bit Googling, and you guys can fact check me because I actually prepared for this one. It is approximate, but if I were to have the same memory with my Sinclair ZX Spectrum, it makes up a little bit medium-sized cruise ship. Like, you built all of these on top. So 10 million times better memory. So this is my appreciation of big data. I'm not actually making any fun of it. It's good. But here's where I start to pivot to something mysteriously, what could be bigger. Let's shift to the decision space. Now, so if the storage is 10 million times better, if the CPU power is about maybe 10,000 times better, we're not going to get into why CPU didn't catch up as memory. But this is a lot of improvement. Are our decisions 10 million times better today? Are we raising our children 100 times better? 10? Worse? So you could start to think that why isn't the knowledge doesn't translate immediately to decisions. So I'll give you one example, which is kind of a good and a sad example. Global infant mortality rate dropped great, 60%, not 10 million times. It didn't go to zero. So what this says to me is that there are many problems. Dow Jones index went 28 times since the picture that I showed. Great, but not 10 million times. So it isn't just information and data. It's also the choice space and the decisions we make. Melissa closed it by humans. Humans make very, very good choices. Very good choices in figuring out that decision space. But now I'm going to pivot to this, what is the other space other than the data? What else is there? So let's start with this a little kind of a game. Again, you could see that I'm a mathematician, so I'm fascinated with numbers, and this goes on and on next 7 more minutes about the numbers. So there's a billiard ball, 16 of them here. And every time you start playing pool, you order these balls a little bit separately. Of course, you don't put stripes next to each other all the time. Everybody have their own methods to do. Think about how many ways you could have actually sorted these balls. Sorted as in how many ways you change it. Like, pick a number, don't say it, pick a number in your mind. I hope that is large, like large. I'm not giving it away. But I'm going to surprise you, actually. So you will also think that, as I'm going to reveal these numbers to you, I want to think that this is not just a game. This is a game, but ordering 16 things is a very real-life problem. If you're a package delivery person, you need to drop 16 packages. You don't know anything about the city, and the order of the packages that you drop matters. Maybe you want to save gas, you want to go home early. There are 16 factorial ways of ordering these balls. 16 factorial. Now, those who you pick the number, I'm going to show you how big that number is. That number is larger than the number of trees on Earth. NASA estimates 3 trillion trees on Earth. 16 factorial, the number of ways I can sort those balls, were 20 trillion. So the way you could sort, number of ways you could sort is more than number of trees on Earth. Now, if you have another visual, the Milky Way, only 300 billion stars in Milky Way. So again, the numbers keeps on going, but I want to show that there are some problems that doesn't look big data. 16 doesn't look big. I could have put in my pockets. So I could have put all those 16 balls in my pockets, but it's not a big data. But the problem that space creates is huge. So if there's a chart, the purple one on the right side shows us in the time progression of the data growth, I would submit, this is my conflict part, I would submit that something else is growing bigger than data. That is decisions, big decisions, the choice space. And actually, with more data, we have more choices. So what is the science of making decisions? And there is actually a science to it, to making decisions. One of them is, before you make a decision, you want to understand the difference between best and the worst possible decision. If you can quickly decide that the difference between best and worst doesn't matter, don't spend time. Pick one, you can recover from that. But if there's a difference between best and the worst, then you need to spend time in something I call algorithms. So while we appreciate data, there is this powerful thing we have called algorithms. Can I represent that blue growing huge data space through algorithms? We did. I'll give you 1 or 2 examples. This is a work that we are honored to do with NBA, National Basketball League. We wanted to solve their scheduling problem. They always did schedule by hand, and they wanted to do, is there a better way to do schedule? So whenever they did by hand, all teams complained. They said, why I'm not playing in the opening night, why I'm not on the particular news channel, TV channel I wanted to be. So we took all of these constraints into a mathematical model, an algorithm. We took all the things that these 30 teams wanted to achieve. They have the desires, what I call objectives, and they have these things that they want to avoid, what I call constraints. We put all of them to a mathematical model. This wasn't very easy. We needed help of a cloud computing infrastructure. Think 30 machines working for a week. Now, 30 machines working for a week in cloud is a lot, because these days there's a lot of things I can do in my laptop. But at the end, the algorithm was able to meet all the constraints, and it met all the desired things that team wanted. NBA is very, very happy with that. Last 3 years, KPMG is releasing the NBA's game schedule. And the reason I gave this as an example, it is not big data. 30 teams on top, 82 games they're going to play. Solution fits to a paper that I can print and hand out. How is it possible that the choice space is huge? It was astronomical, around the order of those trees that I showed. And some of the technology improvements made this possible. Cloud computing, parallel processing. And some of you might have heard this. There is this new thing called quantum computing. Now, we're not there yet for the machines, but in this project, we use something called quantum-inspired algorithms. These algorithms use quantum computing mindset and then go. Again, remember here that the focus is data could be large, but the choice space can be traversed very efficiently through the use of algorithms. I want to give one or two examples and close with this one. So another example that we use is that we have a fantastic team here that's doing portfolio modeling. We have a securitization team. So think about you have 500 securities you want to pick from, or stocks you want to pick from, and you want to pick 10% of it, which is 50. To pick 50 out of 500, there is 10 to the power 69. Don't laugh. You guys are thinking I'm deleted into the numbers. 10 to the 69 ways of picking 50 out of 500. There is 10 to the power 50 atoms on Earth. So the team went into using power of algorithms to find a way to traverse this space way more faster using the algorithmic power. No machine can solve this problem, but algorithms can. So I like to actually close by seeing what can we do with this. Again, I articulated a data space, large, I love it. Big data is my job. But something bigger is that decision space, choice space. There are a ton of hidden problems that are hiding there. I mentioned portfolio optimization. I touched on that NBA. There's a lot of routing, scheduling. You have a budget to cut. Which of the 1,000 programs that you would need to cut? That's an optimization problem. It's not just big data problem optimization. So in closing, I think that what you're seeing here is that UN a couple of years ago came up with 17 Sustainable Development Goals. These are awesome. We need to reduce hunger. We need to gender equality. So this is that 16 billiard ball problem slide. I really submit that there are many problems hiding here that are very difficult. You need data, but not just data. We need to reduce inequalities. I had a pleasure to work in my team here with a bank that we wanted to find credit hidden population and figure out a way to give them credit. To me, this is an inch. I'm not reducing inequalities on the world as UN wants to, but I feel I contributed to number 10. And I see my colleagues here who had contributed to other part. So my ask, like Duncan did, let's be obsessed with one of these. I think that this big data and big algorithm and solution space will allow us to tackle these large problems. Thank you.